Today, we are going to discuss about weighted residual methods, and we are going to start with two methods first, so which is point collocation and subdomain collocation, right? So we will go one by one. So we will go starting with what we discussed last class. So what are the general steps in FEM, and then we will proceed in deriving a particular mathematical model for a simple bar problem, right? So when I say bar problem, it means that the load is acting axially. So always on the axis. Okay. So beam means it is perpendicular to that transverse loading. This is what we discussed last class. These are the general steps in FEM. So first discretization. While you discretize, so you will be having number of nodes and elements. You have to decide how many number of nodes and elements you have to discretize. Then you select a displacement function, whether it's a linear function or a cubical function, whatever it is. That is a selection of a displacement function. Then define a material behavior, what type of material it is, right? So by giving what is the stress strain relation, which is related, stress and strain is related by Young's modulus, right? Similarly, strain displacement relation. So these things we can use to identify what is your material behavior. After that, we derive element stiffness matrix. After we derive an element stiffness matrix, we assemble the element stiffness matrix in a global element for all the elements. Then you apply boundary conditions. Then find the solution for unknown displacement. Then identify what is the stress and strain. At the end, you interpret your results. So these are the general procedure. So when you look here, so whenever you concentrate on this, so if you refer any software, right? So the first step, that is this discretization, this step, right? This step we call it as pre-processing, right? So pre-processing, right? So this is what we call it as a pre-processor. Then from here to here, right? So selection of displacement function, your material property, stiffness matrix, boundary condition, identifying the solution, everything comes under analysis. In ANSYS, they call this as solution. In ANSYS, they call this as solution. And the last one, we call it as post-processing. So interpreting your results. That one we call it as a post-processing. So when you look at the software, any software, you divide this, whatever the steps, into three: pre-processor, solution, and post-processor. So these are the three steps we use in any simulation software. Okay, so it means that up to meshing. So when you have a component, you choose a component, choosing an element, and up to meshing, we go for this pre-processor. After that, applying the boundary conditions, then solving the problem, everything comes under solution. And after you identify the solution, how to interpreting the results, looking after the results, right? So that one we call it as post-processor, right? So these are the general steps. So this is what we discussed last class, right? So today we will start with this weighted residual methods. Okay, this is a powerful way of identifying an approximate solution for a differential equation, right? For any differential equation. So the main thing, there are different types of weighted residual methods. In this, these are the methods, right, which is popular. One is point collocation. Next is subdomain collocation. Third one, least square. And the fourth one is Galerkin's method, right? So now, whatever the element we have in any software, it is based on this Galerkin's method. Okay. So the element matrix and the element stiffness matrix is derived from Galerkin's method because it is easy. So when compared to, and accurate also when compared to the other three methods. Okay. So the first step is you identify from coin collocation, you go one by one accordingly. Right. So, okay, what is the procedure? Right. So you take any differential equation which satisfies the boundary condition. So the differential equation should satisfy the boundary condition. You take an equation, then you assume a trial function. right, for that equation. So the trial function should also satisfy the boundary conditions, right? So trial function is based on a Taylor series. When I say Taylor series, so you call something called as Taylor's series. So when I say Taylor series, it is like something like this: a naught plus a1x plus a2x square plus a3x cube. So it will go something like this. This is what we call it as a Taylor series, right? So we always assume a trial function by considering Taylor series. So which is that will be convenient for solving any type of problem, right? So and that trial function will satisfy the boundary condition, right? So you assume that the function will not satisfy the equation, then identify a error in a particular in that particular trial solution. They will consider that as a residual, right? You consider that as a residual. Now, your main objective is to minimize this residual. To minimize this, we use the different types of approaches, right? So, weighted residual approaches, right? So, hope it is not somewhat clear. So, because I have mentioned something like this. Let us take an example. So, let me consider a cantilever beam, right? So, which is having a point load W at the end, right? So, if I consider this beam, right? If I consider this beam, you know that you have a deflection equation, right? If this is L, so you can able to identify what is the deflection equation here, which is W x square by 6 EI 3L minus X. So this is your main equation for any location. For example, so this is my location where X is equal to 0. This is my equation when X is equal to L. Right? So you know that you will have maximum deflection when X is equal to L. If I put X is equal to L, right, you will get WL cube by 3A. So we know what is this formula. Usually, whenever you have a cantilever beam at the point load at the end, so your maximum deflection will be WL cube by 3EI. But when I want what is the deflection at any point, so because if this is deflecting like this, right? So if I want when X is equal to 1 meter, what is the deflection? I have to substitute X is equal to 1. So to identify what is the deflection here, right? So this is the main equation, right? This is the main equation. So this is the answer for your cantilever beam. Now what I do is I consider y is equal to a naught plus a1x plus a2x square. Let me consider this is my solution. So is this two are equal? So this is not equal. So I say something, this is my solution, right? So I write some equation. I say that is my solution, right? So actually it is not right. The real solution is different from your whatever the function I am taken. This function, whichever I take something, that one we call it as a trial function, right? This is my trial function. So this one, right? Assume a trial function. Something you are assume and you say that is your answer. So you know that is not the real answer. So that you have lots of error. Okay. So let me consider this is y1 and this is y2. So for convenience. So you know that y2 is the real answer. Y1 is something the answer you assumed. So there will be an error, right? So I'm identifying what is the error. So error is nothing but y2 minus y1, right? For example, my real deflection is 3 mm, but I say I assume that my deflection is 1 mm, right? So 3 minus 1, so 2. That 2 is your error. Okay, so this is your error. Similarly, so this is my real function. This is my trial function. Whatever I take, that is the answer. So I am subtracting this 2, you will get an error. This error, the error we call it as residual, right? So error in the function is considered as a residual. So this is what we call it as a residual, right? So my aim is to minimize this residual, right? What happens if I minimize this residual? Automatically, your error will be approximately zero, which means you will get the real answer, right? So to minimize this residual, we are using that different types of approaches. That is point collocation, subdomain collocation, least square, and gather K method. Okay, hope you can understand now, right? So for any problem, any differential equation, I consider a trial function as a result. That is my solution. So based on that, I identify what is the error, which is nothing but a residual. So after I identify this residual, I concentrate to reduce this residual, right? How much I reduced, that much accurate, I will get the answer. I can't make your residual as zero. It is not possible to make it as zero, right? Because this is an approximation method, right? It is very, very difficult to get it as zero. So, but you can bring nearer to zero, around 0.1 or 0.001, something like that. Okay, but not possible to get zero. This all the four methods involved in this piece. So how to minimize this residual? What are the procedures? Right? We have to follow that procedure. Okay. So that's the thing. Before we proceed, so let us derive a mathematical formulation, right? Mathematical model for a simple bar problems. When I say bar problems, as I told you, it is load which is acting axially. Okay. So let us derive it. So let me consider something like this. So you have fixed at one end and you have a varying cross section bar. So you are applying force. There are two forces. One is something self weight, which is Q of X, and another is force which is acting at the end, right? So to solve this, what you do, you going to consider a small strip. Okay. So when I consider a small strip, I will draw the strip alone. So the small strip is having a displacement of del X. Now, on one side, I have a reaction force P of X. On other side, I have a force of P of X plus del P of X. So why we put del P of X is this object is deflecting. It is not an engineering mechanics problem, a rigid body problem. So for a rigid body, reaction is equal to your force acting, right? But for elastic body, your reaction is equal to force plus additional force, which makes your object to deflect. Okay, so that's why we have this del P of X, additional force. Okay, and you also have Q of X, which is like a UDL, uniformly distributed load. Okay, so this is for per meter. So overall force will be Q of X into del X. That is the overall force. Right? So now I say that it is in equilibrium state. I will say left hand side is equal to right hand side. Left hand side, you have only one force, which is P of X. Right? Right hand side, you have P of X, del P of X, and Q of X into del X. Right? So it's the overall force. So left hand side is P of X, right hand side is all these things. You will know that this will get cancelled. Right? Remaining term, I'm putting like this. So you are getting something like this. So del P of X plus Q of X del X is equal to 0. Right? So let me divide by del X. Right? We'll get something like del P of X divided by del X plus Q of X is equal to 0. This del is a simple or very, very small object, small force. Okay. So in differentiation, we call it as D. Okay. So what I do is I'm going to redo like this. So del P of X by del X, I can write it as dP of X by dx. Okay. D by dx. So because very, very small amount, so it is related to differential equation. So d by dx of P of X plus Q of X is equal to 0. Right? This is my term. Okay. So now I'm going to change this P of X. because I am concentrating on my U. U is my deflection, right? I need in terms of U. Okay, so deflection. So for that, I am changing this entire P of X in terms of U. So how to do that? I'm going to use the center of material approach. So let us consider P. What is P? P is a force, right? P is a force. I am relating force in terms of stress. What will get? I'll get, so P is equal to A into stress. Stress is equal to force by area. So in that case, your P is area into stress. Now, stress I can write in terms of your strain, E into strain. Okay. So you know that stress is equal to Young's modulus into strain. So stress by strain is Young's modulus. I am applying here. So you will get E into strain. Right. Now, what is strain? Strain is nothing but du by dx. According to differentiation, your strain is always du by dx. Okay. So which means, so strain is du by dx. Let me substitute this. You will get your P is A E du by dx. Okay. Now substitute this in this equation. Right. Substitute in this equation. So I'll get an equation like this. D by dx of A into E into du by dx plus q of x is equal to 0. Right. So this is my mathematical equation. Right. I am converted this bar, simple bar element to a differential equation. Right. So everything in terms of strength of material, we changed it and we got it as a differential equation. Okay. So why we put A of x? The reason is your area is varying with respect to x. So this area, you have this at this location, you have different area. At this location, you have different area. So that's why we put A of x. Similarly, E of x, you can either put E of x or E. So E of x means your Young's modulus is also varying in terms of your x-axis. Okay. If it is not so, you can just directly put it as E. Otherwise, you can consider it as E of x. Right? That's what I indicated here. So varying cross section of area is A of x and varying material property is E of x. Right? So now we got this differential equation, something like this. Any doubt in this? Up to this?
No, sir.
Yeah. Okay. Now we will proceed with our regular methods. So what is the things we are going to do, right? So let me consider this area. So something like this, right? So just now we derived that. Okay. So can you able to see whether your area is varying? No, your area is not varying. Your Young's modulus is not varying. So in that case, that equation, this equation, I can write it as A E, right? So A is common because x and E is not varying. So d by dx of du by dx, which means I can write as d square u by dx square, right? Plus, instead of q of x there, here you have p naught. So p of x is p naught. They mentioned that. So p naught. So is equal to 0. This is my differential equation for this particular problem, right? So, okay, I got my differential equation. What is my boundary condition? So many times we talked about boundary conditions. So I say that you have to apply the boundary condition in FEM, right? What is that boundary condition? Where is fixed? Where is free? That thing we call it as a boundary condition. So when I say here x is equal to 0 at this location and x is equal to L at this location, at x is equal to 0, so this is fixed in. Do you have u value? What will be your u value? U value is the deflection. What is your u value here? When x is equal to 0. So in this case, your u is 0, right? In this case, your u is 0. So this is my boundary condition. When that we can write it like this, u of 0 is equal to 0. When x is equal to 0, u is 0. Right? Now, when x is equal to L, when x is equal to L, u is not equal to 0. U is maximum. U is maximum. Right? So this is another condition, but you can't apply this, right? So what I do is there is another thing I can do. So do you have any point load here? There is no point load here, right? So previously we discussed something here, right? There is a point load. Okay. So something like this, right? So similarly, so here there is no point load, right? If there is no point load, F, F is what we call it as AE du by dx, right? So from previous step, you can able to see P is a force which is AE du by dx. Okay. So in that case, so this is equal to 0. AE du by dx at x is equal to L is equal to 0. Right? This is my boundary conditions. Okay, this is my boundary conditions. So let me erase this. So because I have it here. So AE d square u of x dx square plus p naught is equal to 0. And you know that this is my differential equation. This too is my boundary conditions. And x is equal to L. Okay. So we apply like this, we identify what is the value. Right. So now what I do is I consider u of x is equal to a naught plus a1x plus a2x square. What is this? This is my trial function. Right? This is my trial function. Okay. So now you know that this trial function, when I substitute in this equation, it is not equal to 0. Right? When I substitute here, u of x is equal to a naught plus a1. So you won't get is equal to 0. There will be an error. Right? That one. Right? When I substitute it, that error, we call it as a residual. Right? After we substitute it, you will get what is your residual. So now our aim is to find out what is this residual. Now we will go for the point collocation method. Right? So we'll proceed with that. So, okay. So point collocation method is whatever the residue you get, you take one point, any point in between the area of your object. For example, if my cantilever beam is from 0 to L, right? I will take a point at the middle, which is L by 2, right? I say that residual at that point is 0, right? I say that residual at that point is 0, so that I can bring it to the nearer to it. Okay, that is the main purpose of this point collocation, right? Right. While showing the problem, you may be able to understand in a better way, right? So what I do is I would choose some point and I say that at that point your residual is 0, so that your answer will be nearer to that. Okay, the answer will be nearer to it. Okay, right. Let me consider this problem. Okay, actually this problem is a 16-mark problem. As I told you earlier, this problem is you have to solve in all the 4 methods, right? That is point collocation, subdomain collocation, least square, and Galerkin, right? So I split up this problem, right? I have taken 2 problems. I splitted it so that you can easily understand in terms of different category. Okay. So let me consider this problem. So the problem they are given as a differential equation d square y by dx square plus 50 is equal to 0. And the limit is from x is equal to 0 to 10. And they are also given what is the trial function, right? Y is equal to a1x plus 10 minus x. Okay, this is my trial function. And the boundary condition is also given. When x is equal to 0, y is 0. When x is equal to 10, y is 0. This is my boundary condition, right? The first step, what you have to do is, if you have a trial function, substitute the boundary condition. It has to satisfy. If it is not satisfied, you change your trial function based on how it satisfies. Okay. So in this case, when I put x is equal to 0, your y is becoming 0. Yes, it is right. So this is satisfying. When I put x is equal to 10, Again, your y is 0. So this is also satisfying. So now I can take that as a trail function, right? If it is not satisfying, then it is different. Okay. So as I told you before, so the trail function is given here. So I am using it. If suppose the trail function is not given, what I do, I have to take a trailer series. I will say y is equal to a naught plus a1x plus a2x square. I take something like this. Okay. So I whatever when I increase my term, when I increase my polynomial, your accuracy will be increasing. But let me limit up to x square. Now what I do, I have to apply this boundary condition. When x is equal to 0, y is 0. What I do? So substitute x is equal to 0 and y is 0. So we'll get 0 is equal to a naught plus 0. So which means I will get a naught is equal to 0. Okay, right. Next, when x is equal to 10, y is 0. Let me apply this. Let me apply this here. So what we'll get? So y is 0. A naught is already 0. We identified. Plus a1 into 10 plus a2 into 10 square. Right. So which means I'll get a1 10 is equal to minus a2 10 square. Right. I am bringing it on the other side. So I can cancel this. So I can say that a1 is minus 10a2. This is my second equation. Now I will substitute this 2 in this equation. I'll substitute this 2 in this equation. What I'll get? I'll get y is equal to a naught is 0. Leave that. A2 is 10. So minus 10 a2. A1 is minus 10 a2 x plus a2 x square. Right? So which means I will take a2 and x outside. When I take a2 and x outside, what I'll get? I will get x minus 10. Right? So you can able to see it is similar to what you got here. Right? Only one negative sign is changing. Right? So negative, of course, the negative always indicates whether it's a downward direction or upward direction. That's it. Okay. But you can achieve the same type of trial function when you apply it if it is not given. Okay. So you can able to see there it is more or less same. Right? More or less it is same. Okay. So this is one way of finding out the trial functions. Right? Okay. So since the data is given, we no need to consider that. So for some problems, they won't give any trial function. In that case, you have to derive something like this. Okay, now I got my trial function. So I want to substitute this trial function in this equation. What I do, I have to differentiate this trial function twice. Okay, so first let me differentiate once, right? So okay, so I'm saying that it has to satisfy the boundary condition. Okay, let it be. So let me differentiate once. So when I differentiate once, what I'll get? I will get a1. Okay, so this will become 10 and minus x square. Actually, if I bring it inside x square, so differentiating x square, you'll get 2x. So this is what we are getting. Again, differentiating, we'll get a1 is equal to minus 2. So a1 into minus 2. We are getting something like this. Now substitute it in here. So what you'll get? So minus 2a1 plus 50. That is not equal to 0. This is my residual. Right? So my residual is this. So R of x is minus 2a1 plus 50. So my aim is to bring this to 0. Right? So that we'll get an accurate solution. Okay. So according to point collocation, look after how many constants you have. So you have only one constant here. Right? Which means in between 0 to 10. In between 0 to 10, you have to take only one point. If you have two constants here, I have to take 2 points. Right? Depends on number of constants. So since you have only one constant, a1, I have to take 1 point in between 0 to 10. The rule is you can take any point, But if you refer any book, they usually take at the midpoint. So we will follow the same thing, because if I take any point, there may be a possibility of reducing. You may get a lesser mark also. So we will always follow the same thing. We will always consider the midpoint. So which means midpoint is 5, right? Midpoint is 5. So I have to substitute x is equal to 5 in this equation. Whether this equation is having any x? No. The equation doesn't have any x at all, right? So no need to worry then. So I can say that minus 2a2 plus 50 is equal to 0, which means I will get a2 is equal to 25. So once I got this, sorry, minus 2a1 plus 50 is equal to 0. So which means I will get a1 is equal to 25. So now what I have to do, I have to substitute in my trial function. So when I substitute it, you will get y is equal to 25x into 10 minus x. This is my answer for this particular problem, right? This is for a single constant. Let us take another problem, another example, which is having two constants. So you will understand in a better way. So let me consider this problem, right? So your differential equation, which is given, right? And they are given a trail function, right? So a1 of x minus x3 plus a2 of x minus x power 5. Okay. And they are also given the boundary condition. When x is equal to 0, y is 0. When x is equal to 1, y is 0. Right? The first step, as I told you, I have to substitute these things whether it satisfies the trial function. When x is 0, y is 0. Substitute it. Yeah, it is 0. Right? It is satisfying this. When x is equal to 1, y is 0. Substitute. It is also satisfying. So both are satisfying. So I can use this as a trial function. Okay. So now let me consider this trial function. So the trial function is y is equal to a1 of x minus x cube plus a2 of x minus x power 5. Right? So I have to substitute this in this equation. So which means I need to differentiate this equation twice. Okay? Differentiate it. So dy by dx. A1 differentiating 1 will x will get 1. X cube minus 3x square. Right? This is 1 and this is 5x power 4. So we are getting something like this. Okay. So hope for letter entry. So d by dx of x power n is equal to n into x power n minus 1. Use the formula. So I think some of you letter entry students will have that problem in that. So that's why I'm writing here. So x power 5, right? So 5x power 4. So we are getting something. This is the formula for your differential equation, right? So when you differentiate. Okay, again we differentiate it. Minus 6x plus a2 minus 20x cube. This is my equation. Now I substitute this in this equation, right? Now substitute it here. What will get? You will get minus 6a1x plus 20a2x cube plus 50x square is not equal to 0, which is equal to r of x. Now look here. So here you have two unknowns, a1 and a2. Which means how many points I have to take? Yes,
2 points, sir.
yeah, you have to take 2 points, right? So I have to take 2 points in between 0 to 1, right? So in between 0 to 1, I have to take 2 points, right? Which means what I have to do, I have to divide this into 3, right? So previously, we have to take 1 point. 1 point means what I have done, I divided by 2, right? So which is 5. So 0 to 10. Now this I have to divide by 3. So in that case, so 0, 1 by 3, 2 by 3, 3 by 3, which is 1. Okay. So I get 2 points now. 1 point is 1/3. Another point is 2/3. Okay. So I'm splitting it equally. Okay. Right. So I'm going to take 2 points now. Okay. The first point is R of X where X is 1 by 3. The second thing is R of X where X is 2 by 3. Okay. So now, so since you have 2 point, I am splitting it, right? 1 by 3. When I substitute X is equal to 1 by 3 in this equation, right? Substitute X is equal to 1 by 3. What will get? Minus 6A, X is 1 by 3, minus 20A2, 1 by 3 cube, plus 50, so sorry, 500, 1 by 3 whole square is equal to 0. Right? When you solve this, you will get a equation. Right? Similarly, let me substitute R is equal to 2 by 3, where X is equal to 2 by 3 here. So substitute X is equal to 2 by 3. So minus 6A1, 2 by 3, minus 20A2, 2 by 3 the whole cube, plus 500, 2 by 3 the whole square is equal to 0. Solve this, you will get another equation. Now I got two unknowns and two equations. Right? Solve this two. Right? So you solve this two, you will get what is the value of A1 and A2. Sorry, I think I will erase this. Yeah. So you solve this, you will get the values of A1 and A2. Substitute in your trial function. Right? Your trial function is 18.53. This is my answer.